Welcome to this hands-on Python tutorial where we take software testing to the next level. If you've ever written a data structure like a stack and wondered how to validate its correctness, this video is for you. Today, we'll build a custom stack class from scratch, and we won't stop there. We'll rigorously test its behavior using one of the most popular testing frameworks in Python, pytest. You'll see how to write real unit tests, automate them, and even calculate test coverage to ensure no logic is left unchecked. From pushing and popping elements to simulating bugs and running parametric tests, this session covers it all. Whether you're preparing for interviews, sharpening your Python skills, or building production-level applications, this tutorial gives you the tools to write better, cleaner, and more reliable code. So buckle up and let's get started with professional-grade Python testing. Before diving into writing and testing Python code, it's important to get our environment set up correctly. In this first step, we install the only third-party library we'll need, pytest. This lightweight yet powerful framework allows us to write simple and scalable test cases for any Python code. We also import standard modules like path from pathlib to handle file writing, textwrap for formatting multiline strings, and subprocess and sys to run shell commands from within Python. These modules are essential for creating, saving, and executing both our implementation and test files dynamically. Setting up your tools properly is often overlooked, but it's the backbone of any clean, automated development workflow. With this setup, we can generate Python files programmatically and validate them using automated tests, a key practice in test-driven development and modern software engineering. Now that the environment is ready, we implement our core logic, a custom stack class. This is a fundamental data structure that follows the last in first out principle, LIFO. The class includes all expected methods: push to add elements, pop to remove the last item, peek to view the top item, and is_empty to check whether the stack is empty. There's also a safe_pop method, which mimics pop but includes built-in safety to avoid throwing errors if the stack is empty. We define our stack as a simple Python list_data, leveraging Python's dynamic list behavior to manage the stack efficiently. Once the code is ready, we save it to a file named stack.py using path.write_text. Writing code this way not only modularizes your logic but also allows for automated testing and reuse, key practices in both academic and industrial software engineering. With the stack class implemented, the next step is writing unit tests to validate its functionality. Here we create a test file named test_stack.py. Inside, we write 3 test functions using the pytest framework. The first one tests the LIFO order by pushing 3 elements and ensuring that pop returns the last pushed item. The second test checks behavior when popping from an empty stack; it should return none without throwing an error. Finally, the third test ensures that the peek method returns the top element without removing it and that the stack is not mistakenly flagged as empty. These test cases represent foundational unit testing practices, verifying functionality, testing edge cases, and ensuring consistency. Saving these tests separately also encourages modular, testable code, one of the best practices in production-grade software projects. Once the tests are written, it's time to run them and verify everything works. We use Python subprocess.run to execute pytest from within the notebook itself. This method ensures our tests are run in an isolated subprocess and that we capture the output directly into Python. Upon execution, we see that all 3 tests pass, indicated by the output 3 passed in 0.01s. This is a strong signal that our stack class is working correctly for the scenarios we designed. The benefit of using pytest here is that it provides clear, readable output and helps catch any issues before they make it into a larger application. Automated testing like this is crucial. It saves hours of debugging and increases your confidence in the reliability of your code. Whether you're working on personal projects or enterprise applications, test automation should always be part of your workflow. In this segment, we take a more interactive approach by manually using the stack to understand its runtime behavior. We initialize a new stack object and push 5 values into it using a loop. Then we use the pop method to remove the top element and print it. Next, we test the peek method to ensure it returns the current top element without removal. Finally, we enter a loop where we repeatedly safe_pop items until the stack is empty. This real-time demonstration visually confirms that our logic behaves as expected. Pop removes the last item, peek reads without removing, and is_empty correctly tracks the state. These quick tests are great for debugging or for quick prototyping before you move to more formal testing. Interactive code like this also enhances understanding, especially for students or anyone learning how fundamental data structures work in real life. To further enhance our stack class, we add a new method called size, which simply returns the number of elements in the stack. It's a small but practical addition that brings real value when you're working with dynamic data. After implementing the method using len, self_data, we write a new test case called test_size. This test confirms that the size is 0 on initialization, increases correctly with each push, and decreases with each pop. We verify that after pushing 2 elements and popping 1, the size is exactly 1. These kinds of incremental feature additions, paired with immediate test cases, embody the principles of test-driven development, a powerful methodology in software design. Testing each method as you go ensures stability and reduces the risk of bugs down the line. It's a disciplined way to grow your codebase without compromising reliability. Now we simulate a common scenario in software development, introducing a bug. We intentionally break the size method by removing its return value. As expected, this causes our previous tests to fail. But instead of fixing the bug immediately, we use it as an opportunity to write more robust, parameterized tests. With pytest.mark.parametrize, we define multiple test cases with various operation sequences, such as multiple push and pop actions, and their expected final stack size. This powerful feature allows us to write one generic test function that can validate multiple scenarios in just a few lines. This not only saves time but significantly improves test coverage and confidence. Catching bugs early is what testing is all about. By simulating errors and systematically validating logic, we build systems that are resilient and ready for production. Finally, we check how much of our code is actually tested using pytest-cov, a powerful plugin that integrates seamlessly with Pytest. After installing it, we rerun the tests with the cov flag, specifying our module name. The result, 92% test coverage. That means nearly all parts of our stack class have been exercised by tests, except for one line, likely related to the recent bug we introduced. Coverage tools like this are invaluable because they highlight untested code and help prioritize test writing efforts. High test coverage doesn't guarantee bug-free software, but it ensures your code has been executed under a wide range of scenarios, which is a major step towards software reliability. If you're serious about clean code and professional software engineering, mastering code coverage metrics is a must. It makes your testing smarter and your code stronger. And that wraps up our journey into unit testing with Pytest. We started by building a stack from the ground up, then wrote detailed tests to confirm its reliability. We explored core testing principles like assertion, edge case handling, test automation, parameterized inputs, and code coverage analysis. By the end of this session, you not only learned how to write a functional stack class but also how to ensure its robustness using automated, repeatable testing practices. This is the kind of workflow professional developers rely on, one that catches bugs early and improves code confidence before it reaches production. If you found this tutorial helpful, please give it a like and subscribe to the channel for more advanced Python and software engineering content. Drop your questions in the comments, and I'll personally respond. Until next time, keep coding smart, keep testing smarter.